My name is MathYou, and in this video we're going to talk about substitution as a continued part of our conversation about antiderivatives, in other words, integration. And the substitution process is going to make it easier, I promise. It's going to look a little tricky, but it's intended to make the process of finding antiderivatives easier when the expression that you're finding the antiderivative of is a little bit more complicated. So as the problems get more complicated, we need tools to make the process a little easier. Substitution is one of those tools. Let's have a look. So, as usual, you can read through these bullets. I think that's fine. I like the things that are being said here, and then really what I want to do is go in and start showing you the process. Maybe the most important thing, though, that we're seeing here, at least I thought it was written here, is, it's that middle bullet that says, in this section we introduce the technique known as substitution. It is simply the chain rule for derivatives in reverse. And that is 100% correct. So let me show you what that looks like. It's not as evident here, but it will be in the next couple of problems that we do. Inside the parentheses here, you're seeing an expression 2x plus 5. It's being raised to the third power. As part of this integration process, I'm going to take the derivative of 2x plus 5. And the derivative of 2x plus 5 is 2, which is a constant value. Let me turn on my pen. Out here, you're seeing a constant value. All right, let me just move down and look at another example problem. Bad example, except that in here you see a 6x minus 7. The derivative of that is 6, which is a constant value. Out here, you don't see it, but it's there, is the number 1, which is a constant value. Let's keep going. This is a little unorthodox, but I promise you I'm going somewhere with this. Blah, 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 that's really scary, don't read that. Well, you can read it, but not right now. In the denominator, in these parentheses, is an expression, 8 plus x to the 6. It's being raised to the third. But what's the derivative of 8 plus x to the 6? Why, it's 6x to the 5. Interesting. Coincidence? I think not. Inside this square root symbol, it says x plus 5 to the 1. We're going to take the derivative of that. What is the derivative of x plus 5 to the 1? It's 5 times x to the 4. Notice the x to the 4. Are there any more? Blah, blah, blah. And then an example, or an applied problem. Okay, so as part of this integration process, we're going to be taking derivatives. And we're going to be taking the derivatives in order to relate part of the integrand to another part of the integrand. Let's get to it. So here's the substitution. We're going to let, well, you don't have to write it over there. Maybe I'll write it over here. Then my hand's in the way. You can't tell. You don't care. I'm going to let 2x, or you could let u equal 2x plus 5. And then I'm going to take the derivative of the 2x plus 5. So that du equals 2 dx. It's not a very good u. Better. My handwriting has not changed since like 5th grade. Okay, so we have this, and we've got this. Now, in the original integrand, I'm going to replace the 2x plus 5 with a u. So let me bring down the integral symbol and put the u in here. We could even put it in parentheses to the third power. The parentheses we don't really need, but that way it helps it match up with the original statement. Now, what have we not addressed? We have not addressed the 4, nor have we addressed the dx. And since this is substitution, we would like to put something in their place. I'd like to swap them out. Well, over here, I see a dx, and I see a multiple of 2. Well, if I'm going to replace 4 dx with something, I can't replace it with a 2 dx. So I think what I'll do is I'm going to modify this equation right here. I'm going to multiply that entire statement by 2. You could even put a little times 2 in there so that we could rewrite this as 2 du equals 4 dx. Now I'm going to replace the 4 dx in the original integrand with a 2 du. Interestingly, the more complicated these problems become, the more apparent the substitution will be that you're doing. However, hopefully you're with me so far. So the 4 dx got swapped out with a 2 du. There's the 2, there's the du. Okay, now let's integrate. We can factor the 2 out of the integration process. Then there's our integration symbol, the stretched out letter S, from Leibniz, from the word summa, which means sum, which means adding things, which we haven't talked about yet. And there's the u to the third, and we're integrating with respect to u now, not with respect to x. There's a u. All right, and we know how to integrate this. Here's the 2, here's the times. We increase the exponent by 1, so it's a 4. We divide by the new exponent, and we don't forget to put plus c. So we've done the integration now. Now what we need to do is back substitute. Let's replace, well, let's simplify first, actually. Let's write this as 1/2 u to the 4th plus c. Now let's back substitute. Let's replace u with what u equals. And what u equals is, where is it? There it is. Yep, it's 2x plus 5. All being raised to the 4th power, and don't forget your plus c. This is the antiderivative of 4 times 2x plus 5 to the 3rd. Really? Yes, really. Could you prove it to me? I sure could. I could take the derivative of this answer, and I better get 4 times 2x plus 5 to the 3rd. And in fact, I would. If I take this 4 and I multiply it out front by this coefficient, then I would get 4 times 1/2 is 2, and I would keep the 2x plus 5, and that's a plus sign where it used to be, and I would decrease the exponent by 1, which makes it a 3, and then I have to implement the chain rule and multiply by the derivative of the inner function, and the derivative of 2x plus 5 is 2. And then I do the 2 times the 2, I get the 4, I keep the 2x plus 5 to the power of 3, and that was my original integrand. So it worked. Not only did I integrate and get a family of solutions because I didn't forget to include the plus c, but then I took the derivative of my answer and I got my original integrand back, which confirms for me that I got the right answer in the first place. I'm so proud of us. Let's try another one. Let's try this one. This is good because it's got a radical in it. The first thing I'm going to do is rewrite this as an exponential, or in exponential form. I'm going to write it as the integral of 6x minus 7 to the 1/2 power. We're integrating with respect to x. However, I'm going to let u equal 6x minus 7 so that du will equal 6 dx, and I'm going to be replacing the 6x minus 7 with the letter u, which means I have to replace the dx with something. And it's this second statement here that allows me to replace the dx with something. But the only thing in my original expression that I still need to replace is the dx. So I'm going to solve this little equation here for dx. Let's divide both sides by 6. du over 6 equals dx. Perfect. Now I know what to replace my dx with. Let's rewrite our original integration problem in terms of u. This is u to the 1/2 power times, not dx anymore, dx is du over 6. That division by 6 can be factored out of the integration process. We can write it as 1/6 times the integral of u to the 1/2, integrating with respect to u now. You know how to integrate these. I'm going to keep the 1/6 out front, times, keep the variable, increase the exponent by 1, which makes it 3/2, divide by the new exponent, which is 3/2, and don't forget your plus c. Let's clean this up a little bit. I'm going to keep the 1/6. I'm going to multiply by the reciprocal, which is 2/3. I still have my multiple of u to the 3/2. We can reduce. 2 over 6 becomes a 1 over 3. Put a little 1 there, a little 3 there. Equals. And multiplying those fractions together gives me a 1 over 9 u to the 3/2. And now finally we can back substitute. Oh, I forgot my plus c. It's embarrassing. And now we can back substitute, replacing u with whatever it was equal to, 6x minus 7, 1/9, 6x minus 7 to the 3/2 power plus c. Who would have thought that in order to integrate, we would need to still be taking derivatives? But as it turns out, that's still a necessary part of the process, especially when it comes to using this technique called substitution. Wow, I just got a cramp in my hamstring. And that is our family of solutions. It's a beautiful thing. More? Do we want more? More examples are helpful. Right, this says that we need to practice. Says that it makes integration simpler. Derivatives are present in the integral. Here are some common substitution forms. Yeah, right, this is helpful. Sort of. This you've seen already, right? Increase the exponent by 1, divide by the new exponent. Don't forget to include the plus c. Integrating 1 over u gives us the natural log. E to the u integrates, giving us e to the u plus c. Now, those are very nice, but the thing that makes these more tricky is that what you're seeing involved in all 6 of these statements, if you will, is u's and f of x's. If they were just x's, all of these problems would be a lot simpler, like this one. Very straightforward, except that it's not the exponent that's the tricky part there, it's the fact that it's u being raised to a particular exponent. So this substitution process definitely comes in handy. You should be aware, however, that it's not always going to work. Substitution is not always the right tool for the job. However, in this section, which is about substitution, it's the right tool for the job every time, which is nice. So just continue accumulating your tools and keeping your eyes open and being sensitive to whatever the situation calls for. Here, what jumps out at me in this problem is the fact that the derivative of part of the denominator, just this part, is equal to the numerator. So when I look at any of these integration problems and I see that the derivative of part of it is equal to another part of it, or the derivative of part of the integrand is equal to a constant multiple of the rest of the integrand, that's what's telling me that I need to use substitution. So here we're going to let u equal 8 plus x to the 6. Therefore, du will equal 6x to the 5 dx. And this one's very straightforward because 6x to the 5 dx is going to swap out directly for that 6x to the 5 dx. Let's make our substitution. We've got the integral of, now this is a little tricky, 1 over u to the third du. So the 6x to the 5 dx, you could think of this as dx over 1, which means that the 6x to the 5 dx is all occurring in the numerator. So you could write this du up here in the numerator. That's just not very typical formatting for an integral. So I have slid the du over to the end of the expression. It is still being attached by multiplication right here. So it's as though it's in the numerator. We just don't usually write it that way. What's happening? Get rid of that. There we go. Okay. Now I'm going to rewrite this integral one more time because it's much easier, I think you'll see right away, to integrate this than 1 over u to the third. Because here, as you well know, we're going to be keeping the variable, increasing the exponent by 1, and then dividing by the new exponent, and including our plus c. From here, there's a little bit of wiggle room as far as how we rewrite this. You could leave it like this and make your back substitution. You might want to write this as negative 1 over 2u squared plus c. And at this point, or in the previous statement up here, we can make our back substitution. U is equal to 8 plus x to the 6. And now it's squared plus c. This negative sign that you're seeing here could go in the numerator, could go in the denominator, or it can go where I've put it, which is next to the fraction bar. All of those are equivalent. So this is a pretty decent variety of example problems for you to be practicing as you get better at the use of substitution as a tool for evaluating indefinite integrals. And I've said indefinite integrals a couple of times. Eventually we'll get to definite integrals, but we're not there yet. Derivative of x to the 5 plus 1 is 5x to the 4, x to the 4, x to the 4. See what I'm saying? Okay, so the derivative of part of this is equal to a constant multiple of another part. That's the indicator that I should use substitution. So let's let u equal Now, if you feel like you got the hang of this, pause the video right now. Try to evaluate this integral by yourself. Once you've got an answer, or if you get stuck along the way, then push play and see this thing play out, or just fast forward to the solution. But I'd love for you to start trying these by yourself if you're feeling capable already. One thing that I see a lot of students forget is to tack that dx onto the end. Especially if you're going forward into a Calc 2 class, you want to be including that dx. The course that I'm teaching at the moment is a BlendFlex. I'm only seeing my students half of the time. We don't spend quite as much time together. Again, this is really a business calculus class, so none of my students are going into a Calc 2 course, I don't believe. So they don't really have to carry forward some of the details of this process with them. But if you're in a Calc 1 class and you're going to be going into a Calc 2 class, especially in person, handing in handwritten solutions, your professor is going to want to see every little aspect of this that I'm writing out. Every plus C, every du, every dx, annotations about substitutions that you're making, okay? Make sure that you're aware of what it is that your professor wants from you, so that you can tailor your solutions and solution process to what it is they're looking for. Okay, back to this problem. I can see the x to the 5 plus 1 is going to get replaced with the letter u. Now I've got an x to the 4 and a dx that need to be replaced. Over here I've got an x to the 4 and a dx that I can use to replace those, but there's this 5 over here associated with them. I don't want that to be with them when I make my substitution. So I'm going to divide both sides of this statement by 5. So that the stuff that I want to substitute into my original integral is sort of isolated, and that's the x to the 4 dx over here. All right, let's make the substitution. And actually, before I do that, let me do a little erasing here, and I'd like to rewrite my original integral as the integral of x to the 4 times the quantity x to the 5 plus 1 to the 1/2 power dx. Okay, now let's substitute. This is equal to, and if you wanted to, actually, before we make our substitution, you could rewrite this one more time. You could write this as x to the 5 plus 1 to the 1/2 power times x to the 4 dx. That way, this and this look like they're ready to be swapped out. If you're comfortable leaving them kind of separated like this and still making that substitution where those two things come together and become the one thing, which is the du over 5, that's fine. Do whatever's most comfortable for you and is going to make sense when you reread your notes. All right, so it's the integral of u to the 1/2 times du. That is much easier to integrate than anything written above it. Let's increase our exponent by 1. Divide by the new exponent. Oh wait, sorry. Made a little mistake. When I replaced the x to the 4 dx, I should have replaced it with a du over 5. So this should say du over 5 right here. Okay. That leads me to want to backtrack just a little bit. What we wrote was correct. It's just better to write it in the correct order the first time. So let me go back. Before I do my integration, I'd like to factor out that 1/5. See, I'm human. I can make little oversights. You will too. Cut yourself some slack. Okay, there's the multiple of 1/5. Okay, now let's keep the variable, increase the exponent by 1, making it a 3/2, divide by the new exponent, which is 3/2, and include the plus c. Then let's clean this up, changing division by a fraction into multiplication by the reciprocal. So that's 1/5 times 2/3 times u to the 3/2 plus c. You can clean up your coefficients and make the substitution all at the same time if you want to. That's what I'm going to do this time. What was the u value again? It's been so long I've forgotten. X to the 5 plus 1. To the power of 3/2 plus c. We're getting good at this, right? Increasing the exponent by 1, dividing by the new exponent, making the substitution. And there are really two substitutions that happen. There's this primary substitution where it's your u value, which in this case was x to the 5 plus 1. So that went in here, and there's the u value. And then there's this secondary substitution process for the rest of the stuff, where we took du over 5 and replaced our other things. That was the x to the 4 dx. X to the 4 dx we put next to each other, and that's what allowed them to be written as du over 5. Even if you want to go in and do these problems, and you're doing them in your homework problems, and then you want to be highlighting them as you go along, or maybe you want to be using different colored pens, or if you're pretty sure that you're going to be making some mistakes and you want to use different colored pencils, if you can find colored pencils that work well with whatever eraser you're using, so that if you make a mistake, you can still erase those colored pencil marks, I highly recommend that. I don't know where it is. Some erasers are better than others. If you've got one of those traditional pink erasers, or just the eraser that's on the end of your kind of run-of-the-mill, that was a long reach, run-of-the-mill mechanical pencil like this one, this is just a little plastic number, this eraser might not do it for you. I use I'm not sponsored by them at all, is Pentel. I use this mechanical pencil. It's very fancy. It's hard plastic. It's got a metal tip on it, and it's got a little metal cap that hides the eraser. And the eraser that's under there is white. And I think it's probably the same kind of eraser as those larger white erasers that have that blue cardboard sleeve around them. I forget who makes those, but I don't know. Again, I say use whatever strategies you can possibly come up with to stay as organized as possible and paint the picture of the process for your mind so that it can see more easily what's going on. And in this case, we are not doing just one substitution, but 2 bits of substitution for every one of these problems. Okay, there's a knock at my door. Be right back. Well, that was a quick visit. All right, what else do I have for you? We might be into... right, so this is just a quick summary of the 3 different situations where you would use substitution. The first is where you have a quantity under a root, or a quantity that's being raised to a power, where if you could take the derivative of that and end up with a constant multiple of the other factors that are involved in the integral, then you would want to use substitution. Or if there's a quantity in your denominator that you could take the derivative of and get some of the other things, or the rest of the things in your integral, use substitution. Or if you have an expression that's an exponent on e, and taking the derivative of that would equal a constant multiple of the remaining factors in your integrand, then you should use substitution. And let's do this one applied problem, and that will be it for this lesson. And we will do a little bit of calculator work in this problem. So here we've got the growth rate of profit from an invention is being approximated by this equation. And what you're seeing here is p prime of x. So this is the growth rate function, rate of growth of profit. So that's like saying rate of change, which is the derivative. So we're looking at the derivative of the profit function. And x represents time measured in years, and the total profit in year one that the invention is in operation ends up being $25,000. Super. We want to find the total profit function. So we essentially have the marginal profit function, and we want to work backwards using the antiderivative or the integral in order to find the profit function. And that $25,000 is going to help us find our C value. And we've only done that once before, and I believe our C was $2. We've upgraded this time. C is going to be $25,000. Maybe. Let's find out. It won't be, by the way, but let's let it play out. So I'm writing with a highlighter. That does not work very well. P prime of x equals x times e to the negative x squared. And we're going to integrate that with respect to x. So p of x will equal the integral of x times e to the negative x squared. We're integrating with respect to x. Now let's set up our substitution. How do I know to use substitution? Because the derivative of this, the exponent on e, is equal to a constant multiple of the other factor involved in this problem. So let's let u equal negative x squared, and then du will be equal to negative 2x dx. And again, if you'd like to rewrite the original integral as e to the negative x squared times x dx, it makes it a little bit more clear having this x dx sort of isolated that we're going to need to isolate this x dx as part of that secondary substitution. So let's divide both sides of this equation by negative 2. And that x dx kind of blurs together, but it is x times dx. And now we're ready to make both of our substitutions. So let's do that and write this now as the integral of e to the u times du over negative 2. I didn't forget it that time. I'm so proud of myself for not forgetting. And let's factor that division of negative 2 out of the integration process. Now that I know how to integrate. Let's keep the coefficient of, or the constant multiple of negative 1/2. The integral of e to the u is e to the u plus c. And now we can make our back substitution. There's nothing to clean up. There's no keep, change, flip or anything. All we have to do is replace u with negative x squared. So this is a family of profit functions. This is not our specific profit function. We're going to find that out next, but if you'd like to put a little note right here that says, this is a family of profit functions. Next, we will find our specific profit function. That would be a good note to put right there. And how are we going to find our specific profit function? I will tell you. Our problem told us that at the end of year one, we had a total profit of $25,000. In other words, P of 1, which is equal to negative 1/2 times e to the negative 1 squared plus c, is equal to $25,000. Well, there's only one unknown in this equation, and that's C. So we're going to solve this equation for C. All we really need to do is subtract -1/2 e to the -1 over to the other side of the equation. So let's just do that. Let's just write it exactly like that. 25,000 minus, or actually we're adding it to both sides of the equation, so plus 1/2 e to the -1st power. And now I'm going to go into my calculator. 1/2 e to the -1 is not a very big number. So this is going to be a little anticlimactic, but I'm going to use my scientific calculator for this one. And I've turned it on, I've hit clear a couple of times. And on my scientific calculator, I'm going to hit the 1. And then near the bottom right, just to the left of my equal sign, is a plus minus with sort of a little chasing arrow in between them. So whatever you need to do in order to get a -1 on your screen, on your calculator, do that. But on this one, now I can see I've got a -1 here. And I'm going to hit the e to the x button, which is above the natural log. But in order to get access to that, I have to hit my second button first, which is in the top left. And then I can hit my e to the x, which is above the natural log, and I get 0.3678 blah blah blah. So that's just e to the -1. Now I have to multiply that by 1/2, or I can multiply by 0.5. So just leave that lousy looking decimal on the screen, hit times 0.5 equals, and I got 0.1839. And as it turns out, very conveniently, this is addition, so you could just hit plus 25,000. And you got yourself a final answer of $25,000 and, rounding it to the nearest cent, 18 cents. So that's our specific C value, which allows us to write our specific profit function as -1/2 e to the -x squared plus 25,018 cents. You are now substitution experts. That pretty much, it doesn't pretty much, as far as the 3 different types of substitution that we're going to look at in the course that I'm teaching, we have addressed all 3 of them. We've seen substitution happen involving radicals, square root symbols, exponents, quantities being raised to a power in the denominator, so the denominators were there, and we've now seen this one last example where we had an expression like f of x. In this case, it was -x squared, and that was a function as the exponent on e. So those are all of the scenarios. I hope that's a good start for you. I hope that you will go back through those 3 different scenarios and refine your notes a little bit about the general plan of attack for when you're in any one of those 3 scenarios, because there's a lot of variety just in each one of those 3. So I don't want you to think that every one of these problems is going to look hyper similar to the examples that we just saw. Keep your eye on the tree, keep your eye on the forest, stay flexible, and be creative. You know, the study of mathematics is in the College of Arts and Sciences. So while mathematics might seem pretty sciencey, there's definitely an art to it. So be creative, get some right answers, and I'll see you next time. Thanks.